Similar triangles and polygons. So this first lesson we're going to talk about, or this lesson regarding similar polygons and triangles, is we're first going to talk about what we did at the end of last class. So the end of last class period, I had you take out a couple pieces of patty paper. And on those pieces of patty paper, I had you first draw a triangle. And it didn't have to be any specific triangle, it could be any kind of triangle. So that's what I'm going to do here. Now, if you were in second period, what I had you do on your first sheet of patty paper was find the midpoints of those triangles, sides. You didn't have to do it for all three, but we'll just do it for two in this exploration. After you found the midpoints, I then had you connect those 2 points to find what we call the mid-segment. So this mid-segment connects the two midpoints, but more importantly, it's halfway down. Now, what I had you do next was I had you copy that upper triangle that I'm going to outline here in blue. So I had you copy that upper triangle onto your second sheet of patty paper, and you compared the angles of this upper smaller triangle with the angles in the larger triangle. And if you were in fifth period, you did something similar. The only difference was instead of finding the midpoints, I had you find the lengths of the sides, multiply them by 2, and then recreate a new triangle. And had you do the same thing. You were supposed to compare the angles and the corresponding sides. I should say you needed to compare the corresponding angles. And the corresponding sides. Lengths. Okay, so that's basically the exploration. Now, what you should have noticed from the exploration is that if I label this A, B, C, D, and E here, and I compare all the angle measures, you'll find that the angle measures are all going to be congruent. It's getting in the way, so I'm going to redraw it. So here we go. That means this angle is the same as this angle. Okay, so that's one thing you should notice, is that all corresponding angles are congruent. Okay? The other thing you should have noticed was the ratios of the corresponding sides are equal. Okay? So all of these ratios are going to be the same. Now when I have multiple ratios equal to each other, we call that proportional. So I'm going to talk about that soon. So that's basically all we did in the exploration, was trying to talk about what makes two objects similar. And so that's the exploration for today. So let's just talk about some basic information about this to get us started. So here we go, some information for us. First thing we need to know is, what is a ratio? I've mentioned this before in class, but ratio is comparing two numbers. So we'll say a ratio of A to B. Okay, so any ratio that compares two numbers, we're talking about A to B. So if I say A to B, I can do an A, then a colon, and then a B. I can also rewrite this as a fraction, A over B. Okay. Now, the importance of this is to remember that the units must be the same in the ratio in order for the ratio to be true. well, they don't have to be, but we like to make them the same. So for example, let's say I had 1 inch compared to 12 feet. That's my ratio. I want to rewrite this feet in terms of inches. So this is going to be the same as 1 inch compared to, well, there's 12 inches in 1 foot. So that means this is 12 times 12 feet. So this is 144 inches. So that's an example of a ratio where the units are the same. And it's very important that you keep the units the same anytime you're going to scale anything. Okay? So now a ratio is just a fraction or a comparison of two numbers. But what happens if I compare two ratios? Well, we call that a proportion. And so this is comparing two ratios. And these two ratios are going to be equal. So if I'm comparing A to B and C to D, these two ratios will be equal. If they're equal, that makes them a proportion. Now there is something that I need to note here, and that's called the cross product property. You might remember this from Algebra 1. But the cross product property basically says if I multiply the values in my proportion across the equal sign diagonally, I should still get a true statement. So I'm going to multiply A and D together, so that gives me AD equal to, and I'm going to multiply BC together, which gives me BC. This will be true every time for every proportion, no matter what. Now, one thing we do say, when I multiply A and D, these are called my extremes. Okay? And B and C are called my means. So when we talk about means, we're actually referencing something called the geometric mean, which we will talk about in a later date. Okay, so next piece of information, actually, we'll talk about the geometric mean right now. We'll just take care of it right now. So the geometric mean is when I have two numbers, A and B, that are both positive. So if A and B are positive numbers, then the geometric mean of A and B is the positive number x such that A over x equals x over B. Oops, I put D. Okay? Now, the really important piece of this is that you notice you have x in the same location. Well, not in the same location, in a diagonal from each other. So if I were to take the cross product of this, this would give me x squared equal to A times B. Which, if I was trying to find x, I would take the square root of both sides, so I have the square root of A times B. So that's the geometric mean. The value of x, the value of the positive number x, is the square root of A times B. Okay, so that's just the geometric mean. All right, so next piece of information, and I hit you with a lot here. We have some properties of proportions. The first one is the reciprocal property. Okay, the reciprocal property basically says if I reciprocate or flip my first proportion, I still get a true proportion. So if I have A over B equal to C over D, if I reciprocate that or flip my A and B and C and D, I still get a true proportion. So if this is true, then B over A will equal D over C. Will also be true. Okay, and we can see this is true by doing the cross product property. If you notice, I cross product the first one, I get AD equal to BC. And I do the same thing with my answer here. So I get AD equal to BC as well here. Okay, so it still gives me the same thing, so I know that it's true. The next one is when I interchange the means. So you remember the means were B and C. So if I switch them, I get a true statement as well. So if A over B equals C over D is true, then if I switch B and C, I should get a true statement as well. So we're going to check this with the cross product property again. So again, on the left, I get A times D equal to B times C. And if I do cross product with the second proportion, I get the same thing. A times D equal to B times C. So I know that this property works. And then our last property for proportions is called has to do with adding a denominator. So if you add the denominator to the numerator, that's our property. So if you add the denominator to the numerator, you get a congruent, or excuse me, not a true statement as well. So if I have A over B equal to C over D, then if I add B to the numerator on the left, I get A plus B over B equal to C plus D over D. Now you're probably thinking, why does this work? Well, think about it this way. In order to add B and A, I would have to add B over B because I have to have a common denominator. So A over B plus B over B, that's the same as just adding 1. And if I add 1 on both sides, instead of B over B, I add D over D. So if I say C over D plus D over D, B over B and D over D are just 1. So I'm just adding 1 to both sides. So my equation is still balanced. So that's why this works. Alright, so that's basically the major properties for our proportions here. So let's talk about what makes two polygons similar. And this is the major part of our video today. What makes two polygons similar? So if you remember from the exploration, I had you find out the two pieces of information that are important for similar polygons using your triangles. You'll notice that, let's say if I have a quadrilateral, a parallelogram, and I label that A, B, C, D, okay? And I compare that, oops, let's do something different. And I copy and paste it and then shrink it. So these two shapes are not the same size, but what's important is they retain the same shape. So if you were to look at the angles, all of the angles are the same value. Got a lot of arcs here. Okay, so angle A is congruent to angle E. Angle B is congruent to angle F. Angle C is congruent to angle D. And angle, not angle D, angle G. And angle D is congruent to angle H. So all my angles will be the same value. Okay? So that's the first piece of information we need for similar polygons. We need corresponding angles congruent. That's the first piece of information. Okay? Now the next thing that we need in order for the two polygons to be similar is we need the corresponding side lengths to be proportional. So remember, in order for two ratios to be in a proportion, their values must be the same. So if I compare AD to EH, that will be the same as AB over EF, which is the same as BC over FG, and the same as CD over GH. So in order for these two polygons to be similar, I have to have both parts. I have to have all angles congruent, and the side lengths must be proportional. The corresponding side lengths must be proportional. If I have this true, I can say that the two polygons are similar. So I would say ABCD is similar to EFGH. And this symbol is what we use for similarity. You'll notice it looks a lot like congruent, the congruent symbol. The only thing is we've dropped the equal sign because they're not the same size, but they're the same shape. So they stay the same type of shape. Okay? So this brings us to similar triangles. So if you remember from the exploration, we talked about what makes the two triangles similar. So if you remember, we looked at the angles. All the angles were the same, but we don't need all the angles the same in order for them to be similar. All we need is two angles. So if I say I have the following two triangles here, so I got this first one, and I've got this second one here. I'm going to label them ABC and DEF. Okay? If I know angle A is congruent to angle D, and angle C is congruent to angle F, I know that the two triangles will be similar. Well, you're telling me why. The reason why is the third angles theorem. If you remember back when we were talking about the measurements of angles, if I have two of the same angle measure, the third angle in a triangle has to be the same because they all have to add up to 180. So that means that angle B will also be congruent to angle E, okay, by the third angles theorem. And because of this, I can then say ABC, triangle ABC, is similar to triangle DEF. Because remember, in order for two polygons to be similar, all the angles have to be congruent. Now, you're probably saying to yourself, well, if all the angles are congruent, that doesn't tell me the sides are proportional, but they will be proportional. This is true. Okay? And we can figure that out in some examples later. The next thing so this is actually the angle similarity postulate. Okay? So you're probably thinking to yourself, are there any other shortcuts that I can use for triangles. Now remember, AA similarity only works for triangles. It doesn't work for anything other than triangles. Okay? But you remember back to congruent, when we had congruent triangles, we had side, 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 angle, side, angle, and angle, angle, side. Well, angle, angle, side has the two angles already congruent. So that's the same as angle, angle similarity. So I don't need to bother with that one. And again, angle, side, angle already has two angles congruent. So that's angle, angle similarity. So with angle, angle similarity, I don't have to bother with either of these two congruency statements. But does side, 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 or side, angle, side also give me similarity? Well, this is not so much congruent as similar. Remember, for similar triangles, all I need is all angles congruent, and I have to have the sides proportional. So for side, 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 and side, angle, side, what this says is if I have my sides proportional, so if we look up at the two triangles in the diagram above, if AB over DE equals BC over EF, and that's also equal to AC over DF, then I have similarity. This is side, side, side similarity. If this is true, then the two triangles will be similar. Okay? And then side, angle, side, you guessed it, if you have two sides similar, or excuse me, two sides proportional with the angle between them congruent, then the two triangles will be congruent. So if I say AB over DE equals BC over EF, okay, so I have two sets of sides proportional. I'm looking at this side here. Actually, let's change color. I'm looking at this side here and this side here. What's the angle between them? Well, the two angles between them are angle B and angle E. So I would have to have angle B congruent to angle E in order for this to be true. But if that's what you have, then you know that the two triangles will be similar. Okay? So those are our three similarity postulates with triangles. Angle, angle similarity, side, side, side similarity, and side, angle, side similarity. And again, the sides aren't congruent, they're proportional. So, proportional side lengths. Okay? It's very important that you understand it's proportional side lengths. Okay, so the last three things I want to talk about are what happens to triangles when I introduce other line segments. And so these are our proportionality theorems for triangles. So the first triangle proportionality theorem we first start off with any kind of triangle. So let's say I have Q, R, and S. This is my triangle. If I draw in a line here, let's say that's TU, okay, if I draw in a line so that TU is parallel to QS, so if TU is parallel to QS, then that means RT over TQ will be the same as RU over US. So the sides will be proportional. So if you have a line parallel to the third side of a triangle, the segments that are produced will be proportional. So if I say RT and TQ will be together, and RU with US. Okay? So, we can also rearrange that. Remember back to our earlier in this portion where we talked about rearranging the proportions, I can rearrange this proportion as well. So if I rearrange this, I could do TQ over US equal to RT over RU. Now again, remember, we have to double check it with the cross product property. So if I cross product these, I get TQ times RU equal to RT times US. And the same thing goes for both. I get it here and here. It works for both of them, which means that these two proportions are true. Okay? So this is the triangle proportionality theorem. The next theorem, second to last one we're going to talk about today, says if I have three parallel lines. Okay, so 1, 2, and 3. Okay? So if I have three parallel lines intersecting two transversals. So here's my two transversals. So let's say this is U, W, and Y, and this is V, X, and Z. Okay? So if I have three parallel lines, so all these three lines are parallel, they intersect the two same transversals, then they're going to divide the portions of the transversal proportionally. So if UW is parallel to WX and it's parallel to YZ, then UW over VX equals, oh, I got this backwards, sorry. It'll still work this way, but I rewrote it the incorrect way that I wanted to. So, UW over WY equals VX over XZ. Okay? Now again, because our proportionality arrangement properties allows me to move it around, play with it a bit, I can also say UW over VX will equal WY over XZ. Both of these are true. Okay? So, next theorem, last theorem for today. Start with the triangle. Let's say it's ABC. I'm going to bisect that triangle. Okay, I bisect that triangle with this angle, with this ray right here, so that this angle is the same as that angle. Okay? If this is true, then that creates a proportion with the segments that it creates, the ray creates on AB. So if here I have AC, here I have AD, I have BD here, and BC here. Okay? What this means is if I have a ray that bisects an angle of a triangle, this is going to be the same as AC over BC equal to AD over BD. Okay? And you'll notice AC matches up with BC, AD matches up with BD. So AC and BC are the sides of my triangle, and AD and BD are the segments that are created from my ray. Okay? Now this is very important to understand. This concept is matching the two things up together. That's what's important about this. Okay, so that's all the information we have. I know it took a long time, but I think it's worthwhile. So let's just go ahead and do a few examples that relate to what you've learned just now. So we talked about proportions. I'm going to show you an example that involves triangle proportionality, okay? I'm going to show you an example for similar triangles, and I'm going to show you an example for indirect measurement. Okay, so let's see here. Let's say I have three over x equal to 4 over 9. Okay? So the thing is I need to find the value of x. Well, my question is how do I do that? Well, we're going to use the cross product property. So I'm going to multiply 3 times 9, and that should be equal to 4 times x. Okay? So 3 times 9, that gives me 27. That equals 4x. Got to get x by itself, so I divide both sides by 4. So my answer is 27 over 4 equal to x. That's not very nice, is it? That's not a very good example, but that's how you do it. It's actually a fine example. It's a very good example. It just doesn't reduce down further than I would like to. So this would be my answer. 27 over 4 is equal to x. Okay? Let's see, another type of problem. Let's say I have two triangles that are similar. Okay? A, B, C, D, E, F. They are similar to one another. Angle A is 30 degrees. Angle B is 15 degrees. Find the measure of angle F. If they're similar, we know that all the corresponding angles are congruent. So that makes this 30 degrees, this 15 degrees. I don't even need to find C, although we kind of are finding C when we find F. So remember, all angles of a triangle add up to 180 degrees. So 30 plus 15, that's 45. Then I subtract this from 180, and that should tell me angle F. So angle F is 135 degrees. Okay? So will angle C. Angle C will also be 135. But that's not what the question was asking. All we really needed to do was find angle F. We inadvertently found angle C. Okay? Now this is also, again, using our idea that the two triangles are similar. All I was given was two angles were congruent. That's all I need for two triangles similar. So that's your similar triangles. That's how I would use that. For the sake of time, we'll do some more practice problems with the theorems that we did in class today. But I will do an indirect measurement example for you. So let's say you are outside, okay? And you want to find out how tall a building is. Now it's kind of hard for you to measure it because you need a big old measuring tape, and they don't have really measuring tapes that measure really tall buildings. So this is where proportional or similar triangles comes in. What you do is you put a mirror on the ground, and you look in that mirror, and you move yourself until you can see the very top of the building in the mirror. So let's say you know you are 6 feet tall, and you measure the distance from you to the mirror to be 9 feet. And then from the mirror to the base of the building is 12 feet. Okay? How tall is your building? Well, that's your x, right? So you have your mirror on the ground reflecting the top of the building into the top of the into the mirror. Okay? So how we do this is we use similar triangles. We use what we call our scale factor. We're looking for the similar or the congruent, the corresponding parts. So since we're looking for the height of my building, I'm going to use the height of the person, myself. So that means x goes with 6. Okay? Next, I'm going to compare. Well, I did x first. X goes with the building, so I'm going to compare 12 to 9. Since I went building then myself, I'm going to go building then myself in the second ratio. And again, they should be equal if I have a proportion. Okay, so now I use the cross product property. So this gives me 9x equal to 12 times 6. 12 times 6 is 72. So that means that x will equal 72 divided by 9, which I can reduce by 3. Well, actually, I can reduce by 9, can't I? 9 goes into 72 how many times? That's right, that's 8. So how tall is the building? 8 feet. Not a very tall building, is it? It's probably like a one-story house, right? So the building is 8 feet tall. So that's an example for you. Okay? So here are your multiple choice and free response questions. Sorry this video is a long one. I'm trying to work it out, but we don't have a lot of time left before we need to test you guys. So here's your multiple choice, and here's your free response. Have a good evening, and we'll see you tomorrow.